Hi everyone, welcome back. Today I want to discuss dynamic programming from a very beginner level in a lot of details. So we will be probably doing um, some basic examples of dynamic programming like using the Fibonacci sequence and then go on to slightly harder examples using 2D dynamic programming problems and so on. And after the end of this video, I want to make sure that you understand how to approach a dynamic programming problem and then solve it fully. I would like to clarify that I assume anyone watching this video has a basic knowledge of how to do time complexity analysis. So, for example, what big O of n means, what big O of 1 means. I will often refer to this as doing something in constant time. And for example, if I have a for loop, so for I from 1 to n, for j from 1 to m. If I do something, then usually the time complexity is n into m, and so on and so forth. The basic time complexity things. Now, given that, we are ready to move into our main content. So the first example we will be looking at is the Fibonacci sequence. It is essentially starting from 0 and 1, and then every next term is the sum of the previous two terms. So 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and so on and so forth. Now the basic recurrence relation for Fibonacci is as follows. You have Fn. How do you calculate Fn? You just do Fn minus 1 plus Fn minus 2. This is all you need to do to calculate the Fibonacci sequence. This is easy to write mathematically, but this might take a very long time if you try to do it programmatically. To see this in practice, let's just code it out. So let me create a new file. So I will code everything in C++. And let's say I have my Fibonacci function, int f. So let me just write a for loop and try to print out the successive values. And here I will set n to, let's say, 30. So let's see what happens when we try to run this. So it is compiled. Now let's try to see what happens when we run this. Oh, segmentation fault. Why is that so? Well, obviously we have not specified the base case for this recursion, so I need to know where my recursion ends. So if n equal to 0 or n equal to 1, let's say I return 0. So instead of our sequence starting from, or rather, okay, this is a bit stupid. If n equal to 0, then I need to do return 0. If n equal to 1, I need to do return 1. Right, so these are the base cases. So f0 is 0, f1 is 1. Now let's compile, run. So these 30 values, it did not break a sweat in computing them. Now let's turn this up to 50. Now let's see what happens. So the numbers start getting larger and larger, and it starts taking much more time to compute them. So let's just take a look at what's happening actually. Let's also try to print out the ith iteration information as well. So let me just stop this. Let us print out this. Now if we run this again, as soon as it reaches 40, 41, 42, now it slows down a lot. So initial values are easy to compute. The later values, well, even for 44, it takes such a long time. Now, why is this so? Well, let's go back to how we are actually computing these Fibonacci numbers. So for example, you want to calculate any Fibonacci number. So for example, f of, let's take a concrete example. So let's say f of 10. Then for that, you recursively call f of 9 and f of 8. For that, you need to this, this. Again, to calculate f of 9, you need to calculate f of 8 and f of 7. Similarly for this. And we can go so on and so forth. Now, all dynamic programming does, and this is actually it, all it does is say that, okay, why am I calculating f of 7 here as well as here as well as here? Why am I doing the same work again and again? So why not, when we calculate f of 7 the first time, let's say this, then I store this value somewhere, and then every time I call f of 7, I just retrieve that value. So for example, this is, let's say, a giant memory I have. As soon as I calculate f of 7, I create a box here and I say that, okay, f of 7 is equal to some number. So let's just say which number it is, 0, 1, 2, 3, 4, 5, 6, 7. So let's say 30. So for the first time, we do need to calculate it. We do need to branch out into f6 and f5. But the second time that I see f of 7, I do not need to branch out anymore, right? I can stop my recursion here. And then I can just access this value and just directly say that, oh, haha, I know that this is 13. So I don't need to go down anymore. So this thing where you calculate the value and store it in some memory, this trick is called memoization. There is no R, it's called. All this means is you kind of maintain a memo of some sort so that you do not recompute same information again and again. So I will not recompute this, I will not recompute this. So my branching will end here, right? I mean, true, but actually it won't even come here because see, when I am going down this path, when I backtrack, right, in my recursion, I have already calculated f of 8. So that means once I calculated this, I had created another box here saying that, okay, f of 8 is actually equal to 21. Now when I call f of 8 here, I actually just go and see, oh, I have already calculated this value, so I don't need to recurse here. So you see that I do not even have to take care of this because my recursion will stop here itself. Now, if you think a bit more carefully, you will soon realize that for every value I, f of I is only calculated once. It may be called several times. Now, it is obviously clear why, if I do not recompute it every time, my complexity should be much better, right? I should be able to do it much faster. So let's take a quick gander into the code as well. So for example, let's say I know that the maximum Fibonacci value I want to calculate is f of 50. So let's say I create a lookup table of, let's say, size 60. And then for till 60, I say that, okay, lookup table of I is equal to -1. So this is a special value, which means that my lookup table value has not been calculated yet. Now we just do one more modification. Here we write that if the lookup table value of n is not equal to -1, that means it has already been calculated, then just return the value. Otherwise, instead of returning this, I say that lookup table equal to this, and then I return. So instead of directly returning this value, I store it temporarily in a lookup table. Actually, it's not temporarily, as in I transfer this value first into the lookup table and then I return the value. So once I have calculated it, my lookup table of n is no longer -1. So every other time I come at n, I will always return back from this case. So let's see if this actually makes our program run faster. It's pretty much instantaneous, right? Now you will notice that there is this minus sign here. Why is that? That is basically C++ overflowing the integer data type. Since Fibonacci grows very fast, even for Fibonacci of 47, the value exceeds the uh, maximum amount that can be stored in an integer. So if I were to change this to long, this, notice that I also have to change this information into long now. Well, then you will actually see the correct value here. So now how to derive a time complexity for this? Well, the total amount of work that we are actually doing is calculating f of I once, right? When I'm calculating f of I am just doing a summation, right? I am just taking f of n minus 1 and I am adding it to f of n minus 2. This step is order 1. Now, a common doubt can be, why is this order 1? I mean, you are doing a recursion tree here, a recursion tree here, you are going down all of these paths. Well, the thing is, they will be accounted for as the cost incurred while calculating f of n minus 1. So what do I mean? So the amount of work I'm doing to calculate f of n is actually quite a bit, but I'm breaking it down into the amount of work I'm doing here at this node, okay? And indeed, I'm going down this path, I'm going down this path, but the amount of work I do here, I am not counting that in my own. That is, for example, going to be counted in this node plus this node and so on. So the amount of work I am actually doing is just this addition step. These things are taken care of recursively. Okay. So I also say that, okay, to calculate fn minus 1, I need to do some work. For to calculate fn minus 2, I need to do some work. But to calculate fn, I'll assume that these things have already been done. And what is the extra work I need to do to calculate fn, which is just order 1. So how many times do we have to do this? We have to do this for n parameters, right? We have to do this for f0, f1, f2, all the way up to fn. So this is the work done for calculating only. So for every one of them, I do order 1 work. So in total, I will do order n work, right? Because n different parameters can be there. But they can be called several times, right? Is that also bounded? I mean, yes, that is. Every function, so for every calculation of fn, I might call 2 different values, right? How many times am I calling fi for some I? Exactly n times, because we have already said that I only calculate fi once. There are n different values of I, so I will only call a function of this form only n times. Now, for every one of them, I will make these 2 recursive calls, which will essentially fetch me that data from the memoization table or the lookup table. That will only be done 2 into n times, because every one of these function calls two other things. We do a lookup there. So we do a total of 2 into n number of lookups. Now, since it's an array, the time for a lookup is just order 1. So here again, we pay a cost of order. So now our Fibonacci just becomes order n plus order n, which is just order. Initially, we had this entire branching tree which suggests an exponential growth, but we reduced that to a simple linear time algorithm. So now that we have already looked at some dynamic programming, now the question is why we have implemented such a long recursive function when we could have implemented something simpler, like the following example, which I believe that most people have already looked at. This does not take this does not really take into account the entire recursive nature of Fibonacci. It just uses a simple constructive building of the Fibonacci sequence. How? Well, I know that every term is the sum of the last two terms, right? So I initially have a first term and the second term, then adding them, I get the third term, then adding the second term and the third term, I get the fourth term, and so on. So here, instead of first, second, third, we just store last term and second last term, right? And then we can just create a new term, or rather the current term, by adding the current, or rather adding the last and the second last term. And then we just set the current term as the last term and the last term as the second last term, so that in the next iteration we can use those two values to build our next current term. The code for that will be something like as follows. Okay, so all the answers match up with our recursive implementation, and it obviously makes sense. And this is usually the implementation that people are introduced to when they do Fibonacci sequences. So the question is, why then go to all this trouble of having a recursive implementation, having this lookup table and everything, when you can just implement this in a simpler recursive manner? Well, I mean, there can be a few advantages to writing out functions like that. For example, when we are writing the Fibonacci in a recursive format, it actually follows the mathematical definition much more closely. Moreover, it is also a cleaner approach, according to me. It is more concise. And we are effectively breaking it up into three specific chunks. So, for example, the first part is where we define our base cases. The second part is the lookup table part, which is actually at the heart of dynamic programming. And then finally, we have our actual transition from the different other recursive calls to my own recursive call, which is the actual definition of the Fibonacci function, for example, here. Now, for iterative formats, it is a bit harder to read for me sometimes. However, there are pros and cons of both. And a thing to note is both are often used. The iterative format, which we did now, is also sometimes called the bottom up approach, since we are actually creating all the smaller values first and then building on top of them, whereas the recursive function is sometimes called the top down approach. So, to give some further example as to why exactly bottom up, right? So, again, you're building up the values from F0, F1, F2. For example, when building the sequence, you are calculating 0, 1, 1, 2, 3, 5, 8, then 13. So by the time you're actually calculating 13, you have already calculated all the values. So 0, 1, 1, 2, 3, 5, 8. You've calculated all the values and then you're calculating 13. However, in the recursive approach, that is really not the case. You are directly calling f of 13 when you are calling the recursive function. So in that case, you are actually forming a recursion tree. So to take a concrete example, let's say f of 13, or okay, rather not f of 13, it should be, I think, f of 7, if I'm not wrong, or f of 8, right? So f of 8 is actually 13. Now when I call f of 8, what I'm actually doing is that I'm calling f of 7 and f of 6 individually in a recursive fashion. So remember the recursion tree that we had up there? Well, we have the top node that we are calling, and then we are calling the children one by one in a recursive manner. And then the recursion tree is basically unfurling, right? It is also calling recursively its own children, and so on and so forth. So the lower values are not really computed. F9 is not computed when we call F10. But when we call F10, it kind of pushes into F9, and obviously at the base cases, there's nothing to call. So now let's look at a different DP problem. So the problem is you are starting at the top left corner and you essentially want to go to the bottom right corner. So the cell marked with green. Now to come here, you can make either of two moves. So there are only two possible moves. You can either go down or you can go right, but you cannot go up or left. So some possible ways can be like this, or another possible way can be like this. Now, how do we actually go about solving this problem? Well, to get a dynamic programming solution, the key idea here, according to me, is realizing that there's nothing special about the green cell actually. You can calculate the number of paths to any cell, not just the green cell. So, for example, this blue cell, in pretty much the same way. There's nothing that special about the green one. So now let's try to look at what actually we will be doing when we are making a journey. So for me, the most important part is what is the last step we can take. So either we can come from top or we can come from left. Now this is going to be the key idea when building our dynamic programming solution. And it is a general strategy indeed that we want to look at either the first step that we take or the last step that we take or something of that sort. So now, since we have already kind of noticed that there's nothing special about the green cell, then let's just try to calculate the answer for all possible cells. Now, we denote that answer by dpij to denote that at the I and jth cell, what is the possible number of ways you can reach that? So that is denoted by dpinj. Now dp here is just a name that I've given, but you could give it any other name. It's just a variable to denote that, oh, we are using dynamic programming. So this is like a dynamic programming lookup table kind of thing. So we often name it dpij, but again, name it any variable you wish. So let me just quickly write down the definition of dpij. So in this grid, for example, our actual answer that we are looking for is actually dp5, 4, right? Because it's in the fifth row and in the fourth column. Now, when I say 5, 4, both are 0 indexed. This is a key important point. These are not 1 indexed, these are 0 indexed. Now, remember that we could only reach the last cell from either the top or the left. So we basically have two choices for the last move that we make. And since we could take basically either of the choices, basic combinatorics tells us that we should basically add them together to formulate our current answer. So how do we exactly write it out? So we write it as dpij is actually the sum of dpi minus 1j, which denotes the number of ways you could go to the top cell plus the number of ways you could go to the left cell, right? So that is dpi j minus 1. Now, usually the main confusion is why is this correct? I mean, I have not calculated dpi minus 1j. I have not calculated dpi j minus 1. Then why, like, how are we getting these values? Aren't these the things I'm trying to calculate? Well, here we do it in such a way that we assume that those two values are already calculated. Now, note that dpi minus 1j basically denotes all the number of paths you can take to the top cell. And basically, when you go from the top cell to the final cell, you have only one option to add to each of those paths, right? It's not like those paths can further branch out. So just writing dpi minus 1j is okay. Similarly, dpij minus 1 denotes all the possible ways you can go to the left hand cell. So starting from anywhere, basically like up, above, whatever place, you can, the first step can be right or down. Note that we are not restricting that. But anyway, we basically denote all possible ways you can go to the left cell, and then for all of them you basically take one more step, right? So the total number of ways you could go left, it's basically that same number of ways you could go left plus one more. So logically it should make sense, but the core question of they are not being calculated yet, I mean, you can think about it in an inductive sense that if they are calculated, I can calculate my dpij. And since I'm calculating them in a recursive fashion, I will have some base case, and like building up on those base cases, I will calculate the entire recursive tree. And so in that process, my dpi minus 1j and my dpij minus 1 both will get calculated. Kind of like how we saw in the Fibonacci sequence, where just calling F10 ensures that you also calculate F9 and F8. So this is how the dpij recurrence works. Now this recurrence is also called the transition. Okay. Now for these two things to make sense, we should also obviously write down the base case. Now what is the base case here? Well, at the starting position, you only have one way of going there, right? So to go at dp 0, 0, there's only one way. You are starting there. So um, yeah, so hopefully that makes sense. At this point, if you have any doubts, I would ask you to maybe rewatch this section a bit, because now I'll move on to the implementation section a bit more and show you how actually coding all these things look like. So let me first delete all this Fibonacci code that I have. So first we will have a DP table, which is essentially our dynamic programming lookup table in this situation. So it will have dimensions max n comma max n, where it basically means that your grid size cannot be more than 50 cross 50 in this example. Now I will also have an init function where I will initialize all the values in my DP table to be -1. Now just to save myself from writing this for loop again and again, I will just use a C++ macro at this point actually. So something like DP, so sorry, something like hash defined for IN. It just means that you are iterating from 0 to n minus 1. So then my code becomes a bit simpler to write. Note that these are not really good practices for programming, but just used in competitive programming environments. And then you can actually define your base case in the init function itself, or you may not. We will see how that turns out later on. But for example, here, if 0, comma 0 is the base case, you might as well just write dp 0, comma 0 is equal to 1. Okay, so now realize that this is a lookup table, or you can think about this as the memoization table, whereas this is actually the recursive function. Okay, I mean, why I'm saying all this, it's just because so that you do not confuse these two names, since I've named it a bit similarly. But yeah, so how you would do this is you have a certain input int I comma j, obviously, and then first you define your base case. So if I equal to 0 and j equal to 0, then we are done, right? Then just return 1. Notice that if you had already said dp 0 comma 0 equal to 1, this base case is kind of handled here automatically. But in any case, so this is now the base case. The recursive case is, or rather, okay, before the recursive case, let's do the lookup table one. So if dpij equal to -1, then we would continue, right? Then it is not calculated. So if it is not equal to -1, then return dpij. Okay. Or else, which is our final actual recursive case, we do dpi, sorry, we do recursive I minus 1 j plus recursive I j minus 1 and then return dpij. Now, this code is how you would recursively implement it, right? Notice that here we are not using dpij directly, right? Because again, we have not yet calculated it. We are going from a top down approach. So we are not going bottom up. So we have not calculated all I minus 1j and ij minus 1, all those things. We are directly wanting the ijth value, and to calculate that, we need to again recursively call the function twice. And then we store it in the lookup table, which I have also named dpij here, and then we return that value. Now, is this enough? Not really. We have missed a couple of base cases actually. So what if the value of I becomes less than 0, because we are doing a -1 here, right? What if the value of j becomes less than 0? So we need to handle those two cases also. So if I is less than 0 or j is less than 0, we return 0. Right? We cannot go outside of the grid. So we just return 0. Notice that we do not have to worry about going above and beyond the grid. So we do not have to worry about going like here or here, because when we are calling the dp recursive function, we are calling using this parameter, like 5 and 4. So when we call it, we basically say, okay, cout dp recursive 5 comma 4 and line, and then we are never really adding anything to the parameters when we are passing it down, so we do not have to worry about exceeding it. So obviously first we have to init to set everything to -1, and this is how it should work recursively. So let's just check. um, so it gives us an answer of 126. Now, is 126 correct? um, uh, I don't want to check now, so let's just check with a smaller value. Let's say 3. Try a smaller value actually. 6. So this is small enough for us to do a sanity check. this is 2, this is 3, oops, this is 3, and let's say this is 4, and this is 5, and this is 6. And I don't think there are any other ways to go, right? So yeah, seems to work. Now let's try to do the same implementation in an iterative format. So here also we will do, let's say, this function. So let me name it n comma m. Now let's look at how we are actually filling up the table. This will give us insight onto how to do it in a recursive way. Sorry, in an iterative way. In Fibonacci, it was easy, right? We are going from left to right. We have this sequence of values. We calculate the left ones first, and then we calculate the right one. For the 2D table, it might be a bit weirder. Right. So to calculate this value, we need to calculate this value and this value, right? Now to calculate this value, we need to calculate this value and this value. To calculate this value, we need to calculate this and this. And so you see that you basically have to calculate values in this diagonal kind of way. How we can actually calculate it is, okay, let me actually do one example. Let us say that we are calculating row first. So we calculate all the values for this row, then all the values for this row, then this row. Will that work? Well, it should, right? I mean, all these values you can calculate directly. There is one left neighbor and nothing upwards, so you can calculate them. We actually, I think, missed that case, did we? Did we account for it? Oh, yes, because when I'm at the edge, I'm making a recursive call here and a recursive call here, but here it is just returning 0. So it is all handled in the base case. So go through the code again once more to make sure that you understand why we are handling all the edge cases as well. Then calculate this. Should also be fine. We have something upwards. We have a 0 to the left. Now what about this? Can we calculate this? Yes, we have here, we have here, we can calculate. How about this? Well, yes, we have these two values, we can calculate, and so on, right? Similarly, for this one, we can calculate this. There's a 0 here, so it's fine. Now, what about here? Well, again, fine, because we have these two. Again, fine, because we have these two, and so on, right? So going row wise and then like one by one, this works. And this is how we will calculate our DP table. So the code will look like something like this. Now here we have to set a base case. We have to set that DP 0, 0 equal to 1. So let's do this here. And now for I comma n, for j comma m. So this is iterating over the columns. Sorry, iterating over the rows, and this is iterating the columns. Okay, so the first loop is going to go first this, then this, then this, then this, and the second loop is like once I come to this row, I have to check out all the columns. Then once I come to this row, I have to calculate all the columns. This is how 2D grids, like 2D, this is how nested loops work. So here we basically do dpij equal to dpi minus 1j, comma, sorry, rather plus dpi comma j minus 1. Here we do not need to have a separate recursive call to some function, right? Since we are building everything bottom up. So by the time we reach this cell, we would have already completed calculating all the values for all these cells. Okay. And now we can directly compute for this. We do not need to make a recursive call and try to find out some other values because we already have them in the DP table. Now, the issue here is, what about the base cases? I mean, this base case is handled well, but what about when we are at the edges? When I is 0 or j is 0, well, we have to handle them separately. So if I is 0, then so firstly, if I and j both are 0, we just skip. So if I 0 and j 0, then continue. If only I is 0 and j is not 0, which is obviously guaranteed because if both were 0, then this would have been true. Then we just do dpij equal to dpij minus 1. Else, if only j is 0 and I is not 0, then dpij equal to dpi minus 1j. And if neither of them is true, that is both are non-zero, then we have this form. Hopefully by now this all makes sense. And we again should do a sanity check, obviously, and then try to see if all the values we are computing are correct. So first, let's print out BP iterative as well. Let's say 2 comma 2. And notice that we do not really need to call init, right? Because we are not depending on all these values being minus 1. We are calculating them off the fly. So it doesn't really matter if they're minus 1 or 0 or whatever. So hopefully these two values will coincide. Oops, we are not returning anything, so let's return BP. So we have to return n minus 1, m minus 1, or actually, I think we should return this only. I'm just saying because you need to make sure that your loop actually calculates n comma m. Right, both of them are the same. So let's say n equal to 36, int m equal to 15. Okay, these are actually very big values. The range will exceed long, or rather int at least. So let's do another sanity check. Oops. Right, both of them have the same value. So hopefully these two implementations are clear and the underlying logic is also clear. At least for me, my main difficulty initially was understanding why this is correct. Like why this is correct. As in, how do we know that these are also correctly computed? And how do we know that combining them like this is also correct? And based on that, well, that is why I later realized that writing down the implementation is a very good idea. Sorry, I mean, writing down the definition is a very good idea. Obviously, you have to write down the implementation, right? Why? Well, then you can use this same term but with different parameters and just assume that it is correctly calculated for those parameters. So, what I mean is, let's say you have some function which takes in a lot of parameters, let's say 3 parameters, I, J, K. You want to calculate this value. So, for example, you do some like a1 into, let's say, fi minus 3 comma j comma k minus 1 plus, let's say, plus, let's say, 35 to the power fi comma j minus 2 comma k. It doesn't really matter what they are, but the point being that if you just assume that these values are true, okay, and this is true. So what I mean by true is, if some god told you how to calculate them, or rather how what the actual true values are, so they are guaranteed to be true no matter what, then if you're sure that this value, this or rather this computation is also true to calculate fijk, then you are essentially okay, oops, what's happening? Then you are essentially guaranteed that this value is correct, right?
because okay, this is true, this is true, you are sure of yourself that the formula is also true, then this is okay. So our focus basically shifts from the actual values that are in these functions to how we are going to calculate the next value. So again, if you have studied mathematical induction, it is kind of the same logic, that if I know that something is true for all k from 0 to, let's say, n, then my if I have the correct calculation mechanism for f of n, which depends on everything which has a lesser value, then it is true. The difference here being that we have more than one variables. But essentially, it's the same thing, right? Because I'm still saying that as long as everything 0 less than k less than n and 0 less than, let's say this is k1 less than k2 less than m, all of these are true, then I can calculate fn comma m in a correct way. Note that the inequalities here, I'm being a bit like lax with the correct symbols, because this inequality would suggest marking this region as correct, but we actually also need these regions. So, but anyway, as long as you get the intuition, I think it should be okay. Again, to kind of see how top-down recursion works instead of bottom-up, you again basically make the same assumption. When you're calling something with n comma m and you're calling two recursive functions, you just assume that okay, these will give the correct result, because after all, they are still following your same combining logic, right? So since you are confident about your combining logic, you just be confident about the fact that these will have the correct calculated values. And then if they are true and if you're confident about your combining logic, then this node will obviously have the correct value, right? So that is basically what is going on in dynamic programming. So hopefully all these implementations are clear. Now, some of you may ask, what's the need of this, right? Even for Fibonacci, we had a constant time formula, right? So if you just Google Fibonacci sequence, um, Fibonacci sequence, go to Wikipedia, and there is this constant time formula where all of these are basically some given numbers like this, and you can find it constant time. For this problem, also we can do it constant time. How? Well, let's take a quick deep dive into a bit of math. Well, what you are essentially doing here is going right n times and going down m times. So go right, or rather, it's the opposite. Go right m times and go down n times. You are basically just mixing up the order, right? Sometimes you are going right, right, down, and sometimes you are going right, down, right. So essentially, you are making n plus m steps. Out of them, some of them are right, some of them are down. So out of those n plus m steps, you just choose which one of them you want to go down. So it's just this formula, right? And this also you can calculate fast. This is just n plus m factorial by n factorial times m factorial, right? This is your combination, permutation combination formula. So to be honest, you really did not need to do all this implementation. You could have just figured out the factorials and then divided and then got this result. But does that mean that dynamic programming is not useful? Well, no. Here is why. Your problem may not be this simple, right? So you might still have to go from this top left to the bottom right corner, but now what if there are obstacles? So what if there are certain cells which you cannot pass? So for example, let's say this cell is blocked. So none of your paths can go through this cell. Or let's say this cell is also blocked. And the number of block cells can be really dependent on your input. Um, So no, a cookie cutter formula like n plus m choose n or something like that won't really help you solve this problem, right? Because that is for a much more generic case. Places where there are obstacles, it's much more different. So how do you approach this in your dynamic programming problem or in a dynamic programming solution rather? Well, note that we are not really changing too much, are we? We are only changing the computation for a few blocks. So, for example, the computation here, it will not be dependent on the left block, right? Because you cannot go left. So this you cannot do. So you are only dependent on your top. For same for this, you are only dependent on your left. You cannot go top. Same for this, you cannot go left. You can only go top. And obviously, you cannot calculate for these two cells, right? It doesn't make sense. If you have obstacle there, you cannot go. So how do we change our implementations then? Well, it's kind of easy. So let's say you have another 2D table here, which states that, so let's say this is basically a Boolean grid obstacle, or rather, let me just name this an obstacle. Oops, should be cool. Now, just add another case that if you have an obstacle at I comma j, then just return 0. Okay, and this takes care of everything, right? Because then you are not calculating the values here, and when you are doing the two recursive calls, maybe from here and here or here and here, they basically return you 0, right? So after doing the recursive call, you hit something which has an obstacle. So then this case won't be true, this case won't be true, but this case will be true. So you just get a return 0 value. How about the iterative case? Well, for the iterative case, it's a bit trickier if you want to make it so. So one thing we could do is we could say that, okay, if there's an obstacle at I comma j, then dpij equal to 0, and then that is it. Continue. And then in these cases, you can make cases like, oh, if this value is an obstacle, then do not retrieve. If this value is an obstacle, then do not retrieve. If this value is an obstacle, then like, retrieve 0 basically, when I mean do not retrieve. So basically, return 0 when I say do not retrieve. So same for this, same for this. There's a lot of if conditions, but if you really think about it, you really do not need to do all that stuff. Why? I mean, you have already calculated all those values, and since you are going in a bottom-up approach, when you are calculating, let's say this, you have already calculated this value, and this already has a result of 0 in a DP table, right? Because 0 means you can never go there. So these will automatically give you 0 when they have an obstacle there, as long as this condition is there. This is necessary. Okay. So this is why having a DP computation is much more important than having a simple cookie cutter combinatorial formula. Often these will work, but if you have these kinds of situations where everything depends a lot on the input, of course, these will work in a lot of problems. But if you have a much more generic situation, like with obstacles in a grid and so on, these simple methods will not work. So hopefully these two problems give you a taste of how dynamic programming works. Now let's move on to one of the most classical problems in dynamic programming, which is called the knapsack problem. So the knapsack problem. Now that we have gone through the basics of dynamic programming, what memoization is, how the recursive approaches work, how iterative approaches work, how to like reason about the correctness of dynamic programming in a very basic way, I will speed up things a bit more and then talk about more of how you come up with such solutions. In any case, let's start with knapsack. So knapsack is like this problem where you have a bunch of items. Okay, Each of them has a weight, so a wi, and then a value, so a vi. So this is weight, this is the value. Now you have a big pouch, okay, or a big knapsack. You want to carry some of these items in the knapsack, but you have to make sure that the total weight does not exceed some capital W, which is the threshold, and you want to maximize the value. So if I want to say a bit more formally, let's say you have a set of objects S. All of them are these tuples Wi, Vi. Okay, and let's say there are n of them for now. So one less than I is equal to n. You want to select a subset of them. So you want to select a subset, could be a proper subset, such that if you take the sum of all Wi where Wi belongs to this subset, this sum is less than equal to capital W. Okay, this is the constraint, and you have to maximize some Vi where Vi belongs to this set you have chosen. So you have to make this max. Okay. So in this version, you can either take an item or you can not take an item. There's no, you cannot break that item into two pieces and take one part and so on. Okay. So why is this important? Well, let's say your W is equal to 20. Let's say you have one item I which has weight 10 and let's say value 6, and another item which has weight 9, or rather, yeah, okay, weight 9 and value 6, and then another item I3 which has, let's say, weight 15 and value 11. If you could take a fractional part, then it makes sense to take whichever which has the highest V by W ratio, right? You take the one with this highest ratio. Once you run out, you take the next one with the biggest V by W ratio, and then just take the fractional part of it if it cannot entirely fit into my knapsack. However, here, for example, if you choose that strategy, then this clearly has the biggest V by W ratio, right? Because the ratio here is 2 by 3. The ratio here is 6 by 10, which is like 2 by, or rather 3 by 5, which is less than 2 by 3, right? Because the denominator is decreasing. But here it is greater than 2 by 3. So it is 2 by 3 plus something. This is 2 by 3 minus something. However, once you take this, then your weight left is kind of just 5. And none of them will fit in 5, right? So you end up with just this 11 value. However, if you take both of these two items and not this one, then your total weight is still 19, which is less than 20, but your total value is now 12. So this is a quick example to show why fractional knapsack is different from 0-1 knapsack. In fractional knapsack, you choose the one with the highest V by W ratio. So for example, this one. And then if you had 5 left, then you would have basically gotten the value 6 by 9, which is the value per unit into 5, right? But in 0-1 knapsack, you cannot divide an item into multiple parts. So how do we solve this problem? Well, the easiest to think about solution is try a bunch of random permutation, like a bunch of random choices, right? Just take some random element, see how it, how see what the value is. If it's not good enough, by some metric. So, for example, let's say you took like 5 different subsets, and you take the maximum, right? Because this seems like kind of an exponential sort of problem, right? I mean, you have to choose a lot of different combinations and then find out which subset has the best value. because such greedy logics won't work. You cannot really like order them in some way and hope that it will work. However, we will still try to employ a dynamic programming solution here. So, what is dynamic programming? Dynamic programming is essentially like a brute force, but you do not recompute the same subproblem again and again. So, let's say we have this function f of x, which takes in some subset of s, and what we want to compute is what is the maximum v I can get from a subset of this x. So I want to choose a subset y from this x such that the summation of w in y is less than w, capital W, and I have the maximum vi summation in y. Okay. So what motivated me to do this? Well, firstly, note that this is kind of what we do want to do for our s, right? So our final answer is actually f of s, right, which will actually give me the biggest subset in terms of sum of values, such that the sum of weights of those chosen items are still less than w. So this is actually our optimal answer, right? So to me, I just thought that okay, we need to have some function wherein I pass the set and that gives me the optimal value. Next, I thought, well, is there anything special about this set s? No, right? It's not like the value, the items themselves have some special property that is only true when all of them are present. So in theory, we can just pick a few values and then create a smaller sub problem out of them, right? So that got me to think that okay, if I pass in some subset of these values as, it should still work. Like the function in theory should still give out an answer which is correct for this subset x, right? Again, I am assuming that some magical function like this exists. Till now, I have not thought about how to implement it. Now, again, in the previous example, I talked about how I want to think about the last step that I took or the first step that I took, something of that sort. So here, what I can think about is, what if I take a certain element or if I do not take that element? So I'm trying to make a choice on a particular element. Okay. So now I'm trying to look at how we can implement this function. So given f of x, okay, where x is equal to let's say x1, x2, x3, and let's say till xk, or rather, okay, the zoom is a bit out. Let me just right away. So suppose we are given this fx. Right. So suppose we are given this fx, x0, x1, x2, x3, so on up till xk. I can basically decide on all of the values whether I want to take them or not, right? So I can do something like loop from, so I can do something like for I from 0 to n or rather 0 to k. What I do here is I basically choose whether that item is there or not. So my answer, so here for example, my answer is 0. Now my answer just becomes max answer. Now there are two possibilities, right? Either I can choose the ith element, so I can be like, okay, um, let me take the value of um, I plus, I will call f with x, but I will subtract from this set xi, right? Because I have already utilized I, the xith element. And this is the case where we take this value vi, or we can also have another case. So we again do a maths with answer where we do not take this value of vi, right? So we just call fx minus xi, right? So in this case, we are taking the value vi. In this case, we are not taking the value vi. These are the only two cases that can happen. Now you might think that, oh, but how are we keeping track of the weight, right? So yes, that is a difficulty indeed. So here we have to attach one more term now into our parameters, which is the weight remaining. So I will call that WR. So notice that I'm trying to simulate how I myself would try to think about this kind of a problem. I would initially maybe not think about the weight remaining, but now that I see that, oh, weight is still an issue, now I would consider attaching that extra parameter into my function as well, right? And obviously, when I now call fx, I mean, when I call this function, I also include wr minus wi, and in this place, I would just include wr, right? Because I'm not actually including the ith item, so my weight is not getting affected. But this still seems like we are doing a lot of extra choices, right? We are trying to pick and choose every item and so on and so forth. So how about we try to do a complexity analysis on this code? So first, how many distinct values can this function f be called with? So how many distinct values of parameters? Well, wr can range in theory all the way from 0 to all the way till capital W, right? And this x can be any subset of S, right? But it cannot have any other element. So it has to be some particular subset of S. How many subset of S are there? Well, 2 to the power um, basically size of S, which is just 2 to the power n, if S has n elements. Now, we will never call the same function with the same parameters twice, right? I mean, if we call it, well, we have our lookup table, and we will just do a lookup operation from our memory. That is how dynamic programming works, right? That is at the core of dynamic programming. So these parameter combinations, this is what we call state in dynamic programming. Okay. So some subset plus some weight, that together forms a state. So how many states are there? Well, each state will have these two components. There are 2 to the power n possibilities for this, and there are capital W number of possibilities for this. So these are the number of states. Now this loop here, this is how we are actually calculating the value for a state. So this is called a transition. So in transition, we basically transit from previously calculated values into my new value. So when I say previously calculated, you might think, but oh, in top down, we have not really previously calculated it. I mean, it's kind of a way of saying this. I'm just saying that from some other different states, we are going to a new state. So that is called transitioning from other states to my current state. Okay. So what is the complexity for this? Well, you have to run your loop k times, which is the number of values present in this subset. Okay. Now, if we just upper bound it by n, so we can just say then that transition is order n. Now, the total complexity is, well, you are basically calculating the value for each state once. So, this into the time taken to calculate every state, which is just order n. So, in overall, you have a complexity n into 2 to the power n into w. This is the total time complexity for this algorithm. Now, I'm not too happy with this. Why? I mean, if you think about it, why are we trying to select each one of them separately? What if we just try to select this x to the power k or not select this x to the power k? Shouldn't that make things simpler? So whenever you see some kind of set where you are selecting items from a set, consider ordering them from 0 to n and then just try selecting the last item or not selecting the last item. That seems like a simplification, right? Then instead of going from I from 0 to k, you just set I equal to k and then just select them, and the rest of the transition does not really need to change. But here, the states reduce drastically. Why? Well, for WR, there are still these many possibilities. We cannot really change that. But what about X? Well, X will always contain, so X will always contain X0, X1 up till Xj for some value of J, right? It will not have a missing element from between. It will not be like X has X0, X1, X2, then X4, X5, X6. X3 won't be missing. Why? Because we are always choosing on the rightmost item. So now, instead of it being a set, X can only have n different values, right? Because for if we ordered S into X0, X1, uh, X2, so on up till Xn, if this is an ordered set, you are just taking a prefix, right? You are just taking a prefix, and number of prefixes available are only n. So instead of having 2 to the power n here, you just have n. And notice how even your transition state, or rather your transition time, is now just order 1, right? Because now you only either take the last item or you do not take the last item. So it's just a choice. It's either this or that, just an if statement. So now your transition time also becomes order 1. So overall time, it becomes n into w. These are the total number of states into transition time for each state, order 1. Before going ahead, I would like you to realize that whenever we are computing a DP, we always have a complexity, or rather, I should not say always, but we usually have a complexity, which is number of states into time for each transition. Now, in some cases, it might happen that depending on the state, the transition time might be different, and then your overall calculation might be different, or something else, like even the number of states might really vary and you cannot calculate it this simply. So those things might happen, but usually this is how we calculate a DP time complexity. Now, I will not go over the coding for this knapsack problem because it's a very well known example. You will find hundreds of codes written there in the internet. But hopefully, the thought process was clear as to how we incrementally made the reductions. First, we just thought, how about we make this function f, which takes in the set s and gives us the correct value. Then we thought that, oh, there's nothing really special about that set s. So, what about we take a subset of that and try to implement it for any such subset, right? Now, when we think about the subset, we obviously have a bunch of items, and then we figured out that okay, if we try to think about what is the last step or what is the first step. Well, we can basically break it down into a sequence of either picking or not picking an item. So we have two cases for that, either for when we pick or for when we do not pick. Now then we realize that this itself is not maintaining the wait condition. So now we made an extra addition to our function where we added a parameter which represented the amount of weight remaining. And when we call the function again, we suitably update that weight remaining depending on whether we have taken or not taken that item, right? Then we got a complexity which is exponential because of subsets and sets. Then we realize that it does not make sense to pick something from the middle or from the end. Like, it's the same thing as picking something from the end, right? That should also exhaustively give us all the possible scenarios. So for any set, if you just order it and first pick the last item or not pick the last item, and then look at the rest of the items, that also makes sense rather than you picking haphazard. So then we realize that the number of possible subsets is just the number of prefixes of this set S. Since the number of prefixes can be only order n, or rather exactly n, the total number of states is also bounded by n into w. And now we do not have this inside loop also. So we just have an order one transition time.
So now that we have gone through a couple of examples, let's try to look at this problem from the Indian National Informatics Olympiad from 2017. This was actually my first national Olympiad, and this was one of the problems that appeared. So there are usually two problems there, so this is one of the problems. Um, it's kind of like a DP problem, but anyway, okay, let's start reading the problem and let's go through it. So the problem is based on Ash and Pikachu. They are going on a route that passes through n cities, numbered 1 to n. So they go from 1 to 2 to 3 to 4 to 5 to 6 to 7 to up till n, so in this order. Now, when they set out, Pikachu has an initial strength, some S value, as well as an experience, which is of 0 value. So as they travel, they may increase his strength, his experience in the manner below. So in each city, Ash can choose either to train Pikachu or let Pikachu battle the gym leader. So gym leader in Ayat City has experience EI. If Pikachu enters I with strength S and decides to train, then his strength increases. So if Pikachu trains, then his strength increases by the cube of the sum of the. So basically, based on some function of his current strength. When I read this sentence, the first thing that comes to my mind is, oh, it is increasing as a function of his current strength, not as a property of the city. So whether I increase my strength in city 3 or city 4 does not really matter. So let's keep that in mind. So let's keep this point in mind. Strength S new is just a function of S old. Okay. So no dependence on which city. On the other hand, if he enters city I with strength S and battles the leader, his experience will increase by S into EI. So his experience E will become S into EI. So he wants to attain the maximum number of experience points that at the end of the journey. So essentially, what we do is we maybe battle a leader, then increase our strength in the next two cities, then battle another leader, increase our strength, then battle a leader, and so on. First things first, is it always good to increase your strength? Well, no, right? Because you want to maximize your experience. Now, then, is it best to always fight the gym leader and increase your experience? No, right? Because it might be better to increase your strength. So, for example, if the experience values gained, like the EI values are, let's say, 0, 1, 1, and then 100,
then you would want to increase your strength here, here, and here, and then battle only here, right? And at least to me, it's not obvious when the strength should be increased or when the experience should be increased. So, worst case scenario, I would like to go via brute force method. So, one thing that I often do in these competition problems, is at least, is try to get an idea from the constraints what kind of solution they are looking for. So here I see that n is up to 5000. So a solution up to n square will work. Okay. So if I just plug in 5000 here, I get something like 25 into 10 to the power 6. As a rule of thumb, in 1 second, you can do up till 10 to the power 8. So this is definitely lesser. So if we can find an n square solution, this will work. Time limit given is 1 second. So now let's try to think about how we can do a brute force and how we can maybe modify our brute force into a dynamic programming problem. So again, we think step by step. So we are maybe standing at city 0, then we go to city 1, city 2, city 3, and so on. And then we reach city I at some point. Okay? Or I should maybe call this city I. And then finally we reach N. So I want to look at what happens when I reach at city I. So at city I will have some strength and I will have some experience value. And we will also obviously have the EI coefficient. Sorry, EI. And this is like current EXP. Now, how do I choose at this city value I what I want to do? What so to do that, it will essentially be either of two options. One, I chain, right? So then my S value increases, and then I process the rest of the items, or I increase my EXP value and then process the rest of the items. Now, when I'm processing the rest of the items, notice that my EXP value currently does not really matter, right? Only my strength matters, right? So either I can do EXP plus I can either do process I plus 1 to n, okay, whereas where my strength value is some s, or and this I'm assuming that I have basically fought that monster, that gym leader, right? So this I will gain from that fighting at the current city, or I just do the same thing, but I have updated my strength. So this will be S new. These are the two possible options I have at I. Now, where did I get the idea of putting the processing of this suffix of the sequence into a function? Right, this is like the key step here, right? Into formulating this DP. Well, how do you come up with it? Well, notice that again, this is another strategy to solving dynamic programming problems. So instead of taking the first or last, I mean, this is also kind of the same thing, but here I'm kind of saying that, okay, suppose I'm trying to process for the ith item. Then how do I process it? Well, I could have either taken the first few things or the last few things, right? I could have either processed according to the prefix or the suffix. But here, suffix makes more sense to me because my strength value is actually increasing in that direction, okay, towards the end point. If I wanted to form a function where I say that, okay, from let's say I have 0 to I, let's say I do something at I depending on what I have done in the previous parts. So then I could have formulated a function like this. I could have said that what is, like, let's say g of 0 to I basically means that what is the maximum experience that I could have gained from processing 0 to, or rather, sorry, I minus 1. However, I need to also mention the strength, right? Because to do anything at my current position, I need to have a strength value, right? Which we are assuming. So, what is the maximum possible experience I could have gained? Assuming that at the current moment I will have strength S. So, I would have done, let's say, some training previously, and then gained up to strength S. So, this is the type of function form that I would have looked at, right? And again, there would have been two cases. I could have either fought here or trained myself more. But then, why will I ever want to train myself? Right? I will always want to increase my experience. Correct? I mean, not really. Because when you are calling this function, I mean, when you're doing this computation, you were actually called with 0 to I and some target strength T. Now, if the target strength T, if you have to do a like strength update or like a training from your current strength that you are iterating on to go to that target strength, it might be that they're different and you do need to do a training to go there. I mean, if you kind of get what I'm trying to say. So you are trying to calculate g of this, and in this you are basically taking the help of g of 0 to I minus 1. Either you are doing a training here, which means that your previous strength would be kind of the inverse function for st. So let's say this is some training function, right? So S new is basically you train your S old, but this would be some kind of T inverse of ST, right? And then you gain some experience, or like, okay, you do not gain the some experience. So this option basically means you are training in the current round, or you could do G0 to I minus 1, and you keep the same training level, which means you are actually doing an experience upgrade at the current position. So these are two different ways to think about it. Okay? The function f means that right now I have strength s. What is the maximum experience I could gain with this strength s starting from now, from the next item to the last, so the suffix. And in this city, I'm going to either do a strength upgrade or a experience upgrade. And this is given that I have processed from 0 to I and the strength ended at I is ST. What is the maximum experience I could have gained? For that, either you can train at the current level, which means at your previous city, your training strength must have been something like this, right? So, what is the maximum XP you can get out of here? Or you could have done a gym leader battle and gained XP. So, you would have gained ST into E of I. But then, even at the previous city, you needed to have this strength, right? But the issue is T inverse is not that easy to calculate. And I mean, you could work your way around it, but it's a lot of trouble. And I feel, at least for me, calculating T inverse is a lot of more trouble that I would want to go to. And so, thinking about the suffixes here makes more sense. Now, the second observation, okay, before going to the second observation, let's try to see if this is of a suitable time complexity first. I hope you can reason already about its correctness, right? We are exhausting all our choices. At the current city, we are either training or battling, and this is how it would happen as long as we consider that, oh, f of something always gives me the right answer. So the suffix information will give me the right answer. Based on that, how can I build the information at the current city? So obviously, the first parameter can be any of the n possible suffixes. So for the first parameter, your option is basically n, like the number of suffixes can be n, right? What about the second parameter? Well, it could be any strength, is it? So strength values are up to 10 to the power 9. So yeah, something of the order 10 to the power 9. But that is not really correct. And this is, I think, the main observation extra required in the problem. Your strength values cannot be just anything, right? You have some starting strength value, SI, SIN, and then your next strength value will be something like TSIN. Then your next strength value will be of this form. And you can only compose this function n times, right? Because you can only train at most n times. So there are only n distinct strength values. So you can basically do a pre-computation and figure out all these different strength values, just like apply this function again and again. So this whatever cubing with its digits and so on. So now instead of 10 to the power 9, you only have n choices. It can be only one of the strength values, right? So here we technically now have n square states. And transition time is, well, at the current city, you decide what you want to do. There are only two options. You either train or you do not train, like you train or you battle. So there are only two options. So just order one. So this gives rise to an n squared d. So let's try to code this out. Again, I will try to code it out in both recursive and an iterative manner. So let's read the input format. Initially, I have n and s in, and then the next line contains all the EI values. So let's try to code it out. So I have max and to be given to be 5000. So usually we do just a bit more extra just for a safe buffer region. Then firstly I will define a long type. So LL, so LLDP max n, and then I have my main function obviously. So here I will take in n, and let's say LLSI, SIN, and then I will take in all my experience values. So let's say I have these values as well. So I take in all my experience values. Now the main part, let's say we have to do, first we do an init function, or rather first you have to compute this history thing, right? Increase its strength by cube of the sum of the digits of its current strength. So let's say I name this function, let's say t of n. So I take in s and I will return the new value of s. So let's first calculate the sum. So it's sum 0, and then we have, let's say, like we want to extract the digits. So let me make s copy. Let's copy to s while s greater than 0. My digit, my digit is just s mod 10, and then I add this to sum, and then I divide s by 10. Then my final answer, what I return from this function is s copy plus sum, rather like cube, right? So sum into sum into sum. Okay. Now note that while I'm implementing, it does not make sense for me to keep track of all the different sum values. Instead, I could just say that how many times I've done the strength upgrade, and that will uniquely determine my actual strength at the current moment. So just to save time to not recompute this again and again, let's say I have another array, strength. So let me just call this TS, like basically composing T on top of S. And we can compose at most max n times. So I will first compute this. So TS, if I've only done 0 strength trainings, then obviously my strength is just Sn. Otherwise, if whenever I is greater than 0, Ts of I is just you pass in Ts of I minus 1 into the T function, right? Which is the training function. Then you have dp recursive, and this will take in the city I'm currently in. So I, to represent that I to n, the suffix, I will just take the ith city. So this will just be like city and the number of times I have trained. So let's say num trained. So the strength is just ts of num trained, right? Now I have two choices. Now obviously if city is greater than n, so we need to store this n outside actually. Whenever city is greater than n, greater than equal to n rather, because it is 0 indexed, I will return 0, right? We cannot gain any more XP. So again, what is this function doing? How much XP, or rather how much experience I can gain from city to n, where I have already trained num trained number of times. Right? My current experience does not really affect the function at all, right? If I'm at city I, however much experience I've gained from 0 to I, that does not affect how much experience I'll gain later on. Only my strength affects it. So that is not a part of our parameter. Now, the base case is handled. Now, the recursive case, well, there are two options, right? Either I do dp recursive city plus 1, so I go to the next city and I actually train here. So now I'm trained plus 1. Or what I can do is I can do a battle here. So in that case, I will basically be gaining strength into E of city XPs. Plus, I do the recursive call to city plus 1. But in this case, I do not train, so num trained remains num trained. And then I finally print out the value of dp recursive with city 0 and number of times trained also 0. Now we haven't yet done the lookup table, so let us do that again. So here I first initialize I have dpij equal to -1 as we usually do. Now here the lookup table state is if dp city strength is not equal to -1, then I return dp, or rather this should not be strength actually, this should be num trained. dp city num trained. Otherwise this is actually dp city num trained. And then we return this one. Let's see if this works. So again, compiles. Let's see the output it produces. Right, 390. So this works, right? At least on the sample output. So let's try to run it in the submit. So let's put it in C++. So this works. Okay. Now, how would we implement this in a iterative fashion? Well, again, to calculate DP city and num trained, earlier we had everything to the left and upwards we need to keep calculated. Now we have to keep everything to the right and down calculated. Okay. So our loop order effectively changes. So let me create another function. Actually, in this case, we do not really need to have any inputs. We will calculate everything from the ground up. So here I need to have the outer loop basically representing the city, let's say. So the outer loop should go from n minus 1, city greater than or equal to 0, city minus minus, and let's say the inner loop represents the strength. Now note that iterating on the columns and then rows or rows and then columns did not really affect even in our last example. It will not affect even up in even this example. Try to reason on your own why the ordering of city or strength will not matter. So, for example, I can take strength to, or rather, let's say, unchained or consistency. Right. So here there are two cases. So my DPIJ, or rather, I should say DP city num trained, should be again the same thing, max of DP city num trained. So city plus 1. So these are the transitions, mind you. So I have to calculate strength here as well. So this should be strength into E city plus EP city plus 1 not trained. Right? Basically the same recursive formula that we had derived. Okay. Now obviously the base cases are not handled. So what can the base cases be? Well, one way I like to think is what happens when these exceeds the bound. So the first base case is if city equal to n minus 1, then obviously I can only gain this amount. There's no point in training, so dpij, or rather city num trained, will only be strength into e of city, right? There's no point in doing any of these other recursive calls because they will be out of bounds. Else, the other case is if strength num trained equal to n minus 1, then we cannot train it anymore. Then again, the same thing. We should just have this. But if you think about it, this case is a bit nonsensical, right? In the sense that you can never actually train n minus 1 times without reaching city n minus 1. I mean, training n minus 1 times means you have trained at 0 all the way up to n minus 2. So, yeah, this base case is not that important, but you should still include it. Otherwise, you might run into out of bounds error for this case. If both of them are not true, well, then this should be the case. And finally, we return dp0, 0, right? That is what our final answer is. We are starting at 0 and we have not trained at all once. So instead of dp recursive, let me change this to dp iterative without any parameters. And it should hopefully give us the same result. Yeah, let's try submitting it again. Notice that this time we are only doing the iterative format. So let's try submitting this. Right, so this worked as well. So notice that here our time taken is actually less than half of our previous submission. Well, that is because recursive calls take a lot of function overhead while iterative is much faster. You're just doing two loops, and due to some other reasons like cache locality and etc., this is much faster than recursive calls, and that is why in competitions we often want to do iterative implementations rather than recursive because they can often take a lot of time. There are, of course, other pros and cons of recursive and iterative that I will go through later. Hopefully, this example made a lot more sense now, starting from how I approached the problem, how I broke it down into the key steps, and how it's not really that difficult to come up with a DP solution. Now, these kinds of problems are often categorized under a broad knapsack cover because they are also like 2D DPs where we are basically doing an order one transition from one state to another. And we are kind of either picking an item or not picking an item, right? So here we are either training or not training, like either training or battling. So we have like two choices. And there is a bit more complexity here because we also have the strength updating on its own and so on and so forth, but it kind of follows the same pattern. So hopefully this made a lot of sense. Notice that handling base cases is a bit more weird in iterative in some way. In recursive, it is much cleaner. Again, those kind of fall in iterative versus recursive, whichever you want to do. I usually like recursive implementation because they represent a lot more clearly how I actually write down the formula when I'm thinking about the recursion, or rather when I'm thinking about the dynamic programming. But yeah, oftentimes you have to implement in iterative to make it pass in a competition problem. Otherwise, if you think about it from a non-implementation perspective, we are doing the same thing in the mathematical sense. So this was one another example of actual competition problem where we can use a dynamic programming solution. Again, I want to stress this once more, but the key point here is just assuming that this function will return me the true value. Same for this function that will return me the true value. This is actually not that much of dynamic programming as recursion, but it's a key aspect of dynamic programming when you are formulating at least. Do not get lost into all the nitty gritties of the recursive calls. That will only block you and prevent you from figuring out the solution. Just assume they are true, or rather, just assume that they follow the definition you have made, and just ensure that if they are true, then the way that you combine also satisfies the definition that you have made.